Alright, in this section it's about using trig identities or manipulating different aspects of the trig functions. They become very powerful in the sense that you can write them in a bunch of different ways. So going back to some of the beginning ones, we have the Pythagorean identities, which this is just sine squared plus cosine squared. Sine squared plus cosine squared is 1. Of course, I could also subtract it over and get cosine squared minus sine squared. I could subtract this one over and get sine squared equals 1 minus cosine squared. Now these you get by just dividing each one of these by, in this case, by cosine squared, or sine squared, I mean. In this one you get by cosine squared. These are just another way to define the six trig functions. You can also define the tangent as sine over cosine and cotangent as sine over cosine over sine. Even and odd functions. These are all stuff from earlier in the previous chapter. Now, what we're going to do is we want to manipulate this side of the equation to become the other side. So what we're trying to do is you want to show that the equality is what's true, right? So you start with this side. So we're doing little proofs. This is what you want to prove. So you start with one side, work to the other side. Does it matter? No. But the one thing you don't want to do is you don't want to keep putting the equal sign in and going down the two sides. That's a common way that people do it, and it's wrong. Because this equal sign, anytime you write this down, if you wrote this down right away, what that means is you know this is true. When you're writing proofs, you only can write down things that you know true. So let's do this one, and you can see how it's done. Alright, so let's try number 30. Cosine x times tangent x minus secant x minus x, make sure we put the minus in there, is equal to sine x minus 1. Now, of course, what we're doing here is that we're trying to prove this identity. So the thing that we don't know is the equal sign. That's what we don't know. Now, one common way you might see people is that they write both sides down as they go, but that's wrong, because each thing you write down has to be true, and the thing we don't know is if it actually is true. So what we do is we start this. So what we're doing is writing a little proof. So to prove, that's what this is. That's what we're trying to do, is prove this. And then here's our proof. So what we do is we start with one side, cosine x, tangent x minus secant minus x equals. Alright, so now we want to keep this as linear as possible. So if I could write this in one long line, I will. So the first thing I'll do is, if I go back, and I can see that under the even and odd identities, that I get that this is an even function. So that means that I could rewrite it cosine x tangent x minus secant x, just like that. Now what I'm going to do is I'm going to do the reciprocal or quotient identities. So put in what tangent actually is, right? Another way to write tangent is sine over cosine. Another way to write secant is 1 over cosine. So I'm going to go cosine x sine x over cosine x minus 1 over cosine x equals. Now we could do this two different ways. I could distribute the cosine. That's a good way. I could combine these two because this is just subtracting fractions. But either way, it's going to give me the same thing. So let's do this by distributing the cosine. So this would give me, it's going to be a little long, so I'm going to move it down here. Sine x over cosine x minus cosine x times 1 over sine or cosine x. These divide out, and that leaves me sine x minus 1, which is what we're trying to prove, and that's the end of our identity. Now I could have, a lot of these identities have a couple different ways, so I could have done it like this. I could have had cosine x and then combine this as sine x minus 1 all over cosine, because that's the definition of adding fractions or subtracting, right? Plus and minus b over c is a plus or minus b all over c. Since they have a common denominator, I can then, just write it like this and then divide it out, and I still end up with exactly the same thing. So you only have to do it one way, and this is the way we went with. Notice that I started on one side. I made sure that each step was justified by something, and I ended up where I started with. Alright, so now let's try this one. So again, like I'm saying, this is you want to show this equality, and again you have to assume that this piece, the equal sign, is the thing that you're proving true. So start with one side, and then you go to the other side. Alright, so let's do number 32. And this one is sine x plus cosine x squared equals 1 plus 2 sine x cosine x. Now this time, again, we want to get from here to here. So this is what we want to prove. Right? This is right here, and here's our proof. So I start off with one side, and I want to work my way to get to the other side. Now this time, I'm going to rely on something that from algebra. So all those formulas that you've ever done with algebra, like FOIL, perfect squares, difference of perfect squares, adding fractions, anything that all comes into play. It's not like you can forget all that. So if I do that, I'm going to use, just as a reminder, I'm going to use this one right here where it says a plus b squared is equal to a squared plus 2ab plus b squared, this special form of squaring binomial, because this is really like a binomial, right? Well, it's two terms being squared. So I'm going to use this. So I get the first one squared, sine squared x plus 2 sine x cosine x plus cosine squared x, like that. Now if I go back to the Pythagorean identity, I see that these two add up to 1, and I have exactly what I'm looking for. And we have our identity shown. Alright, in this section, these are some sum and difference formulas. You can read in the book how they're derived. It's pretty interesting about taking the angle in the circle and manipulating it two different ways and using the distance formula. But we'll just do a couple little examples here to apply them. So this first one, of course, it doesn't look like it's a difference or a sum, but when we do the example, you'll see that it does. So let's do that example. Alright, for this one, we're going to use these identities. These are the sum and difference of the angles identities. There's a lot of them. So for number 8, right, we have the tangent of minus pi over 12, and we want to simplify this as much as we can. Now, at first it might not look like this is a sum or a difference, but if we play around with this term right here, we might be able to get it to be a sum or a difference. Now, really the pi isn't going to play a part in here. It's really about decomposing the fraction 1/12. Now, I do know things like pi over 3 and pi over 4, right? Pi over 6 and pi over 2. Like that. So there are numbers that when we break down fractions, we could get a 12, right? So like, for example, if I had pi over 3 plus pi over 4, and I added them together, this would be 4 over 12, and this would be 3 over 12, which would give me 7 over 12. If I subtracted those two, this would be 4 over 12, and this would be 3 over 12, which would give me negative 1 over, or positive 1 over 12. So if I flip these around, that could give me this right here. So if I go pi over 4 minus pi over 3, that will give me, get a common denominator, right? So this is a 3, that's a 4 over 12. So this gives me 3 minus 4 is negative pi over 12. So I could rewrite this as the tangent of pi over 4 minus pi over 3. Now what I could do is use the correct identity, and that gives me the tangent of pi over 4 minus the tangent of pi over 3 all over 1 plus tangent of pi over 4 times the tangent of pi over 3. So now the only thing is now we have to know what these guys are. So this we could go back to our little table that we've always that I always make like this, right, where you put in your angle here and you go 0, pi over 6, pi over 4, pi over 3, pi over 2. Put the sine of theta here, cosine theta, and go 0, 1 over 2, square root of 2 over 2, square root of 3 over 2, 1, reciprocal because of the 90-degree thing, right? Formulas. And then, so then you can do the tangent, right? Tangent of, this one would be sine over cosine, which is 0. This one would be 1/2 over 2, which is 1 over the square root of 3. This one is just 1. This one is halves divide out, so this is just square root of 3, and then this one is undefined. So we can do the tangent. So now we can simplify this. Pi over 4 tangent is 1. This one is tangent of pi over 3 is square root of 3. This is 1 plus 1 times square root of 3, so this is 1 minus square root of 3 all over 1 plus square root of 3. Like that. Which I suppose we could rationalize the denominator if we want to be really fancy and get it as 1 minus square root of 3 times 1 minus square root of 3 over 1 plus the square root of 3 times 1 minus the square root of 3. This would give me 1 minus 2 square root of 3 plus 3 all over difference of perfect squares, 1 minus 3. So this would be, what, 4 minus 2 square root of 3 over negative 2. So I get negative 2 plus square root of 3 for my solution to that problem right there. Now in this one, what we're going to do is we're just going to simplify it so it's just in terms of sine and cosine. Alright, so number 10, let's do sine of x plus pi over 6. So we can break this up using the sum formula for the sine. Sine of x times the cosine of pi over 6 plus cosine x sine of pi over 6. So sine x, now the cosine of pi over 6, we can go back and do our little table if we always want. If you're never sure, this is, you know, if you want to do it by hand like this, right? You have 0, pi over 6, pi over 4, pi over 3, pi over 2, sine theta, 0, 1, 2, 3, 4. You do this with a pencil, it works better. Divide by, take the square root. Square root of 2 is, square root of 4 is 2. Then divide by 2. And you get that, cosine 0. So then write these backwards because you have the 90-degree rule. 0. Yeah, this is, sorry, 1, 0. So now just pi over 6, that's all we really look for, is what the cosine and the sine. So sine is 1/2, cosine square root of 3 over 2. So this is square root of 3 over 2 sine of x plus 1/2 cosine x. And we have our broken up into sines and cosines. Okay, so here are, these are some formulas that crop up quite often, the double angle and the squareds and the square roots. In this first example, you'll see how we can find the double, when we know a particular one, we can find the double angle formulas by using these formulas. So let's do that. Number 6. If the cosine of x is equal to 2 over 3 and x is in quadrant 1, we're supposed to find sine of 2x, cosine of 2x, and tangent of 2x. Okay, so, well, to do this we need the sine, the cosine, and the tangent. So let's figure out what those are, and that's just that SOHCAHTOA stuff. So let's draw a little triangle. So here's our right triangle, here's x. Since the cosine, that'd be adjacent over hypotenuse, so that would make this side 3 squared minus 4 squared, square root of 5. So that tells us that the sine of x is square root of 5 over 3, and the cosine of x, well, 2 over 3, we already did that. Tangent of x is square root of 5 over 2. So now we just use these three things. So the sine of 2x is equal to 2 sine x cosine x, which is 2 square root of 5 over 2 and over 3 and 2 over 3. So this would give me 4 square root of 5 over 9. Cosine of 2x is equal to the sine, or cosine squared x minus sine squared x, which would be 2/3 squared minus square root of 5 over 3 squared. So that would be 4 over 9 minus 5 over 9, which would give me negative 1 over 9. Now the tangent of 2x would be 2 tangent x over 1 minus tangent squared x. So this would be 2 times the square root of 5 over 2 and 1 minus square root of 5 over 2 squared. So this would be square root of 5, because those divide out. This would be 1 minus 1, 5 over 4. So that would give me square root of 5 over negative 1/4, which is negative 4 square root of 5. Alright, in this one, what we'll do is we want to find all 6 trig functions, but notice where they're putting a restriction. This is going to come into play based on, it'll tell us what the sine, SIGN of the sine and the cosine and the tangent and all those things are. So that's where this comes into play, is what the sine, SIGN, not SINE. And so we'll take this piece and we'll apply, well, you'll see that it's this, we can use this one right here to figure out our cosine. It really leads to this one right here. These are really this kind of the same formula. But let's do that one. Number 10. We want to find all 6 trig functions if we know that the cosine of 2 theta is 1 over the square root of 2, and theta is between 270 and 180 degrees. So in other words, quadrant 3. This we could rationalize as square root of 2 over 2. Alright, so we do know that the cosine squared of theta is equal to 1 plus cosine of 2 theta all over 2, which would mean that our cosine of theta for this particular example would be 1 plus square root of 2 over 2 all over 2, or rationalize 2 plus square root of 2 all over 2. I mean, not rationalize, but get a common denominator, which would be cosine squared of theta is 2 plus square root of 2 all over 4. Now we can take the square root. So cosine squared of theta, or cosine of theta, is plus or minus square root of 2 plus square root of 2 all over 4, which is square root 2 plus square root of 2 all over 2, like this. Now, because we know it's in quadrant 3, the cosine is negative there, so we know it's not positive, so it has to be the negative one. Alright, now once we know that, we can go back to the SOHCAHTOA stuff, And we know that the hypotenuse is 2, and this side is 2 plus square root of 2. So this side would be square root of 2 squared minus this thing squared, which is just 2 plus square root of 2, which simplifies to 2 minus square root of 2. Now we can just find everything. So we have the cosine, that's this one. And again, this is negative, and it's in the third quadrant, so this would have to be negative, because both sine and cosine are negative in the third quadrant. So we know that the sine of theta would be negative 2 minus square root of 2 all over 2. Opposite over, hypotenuse. And tangent of theta would be opposite over adjacent, so this would be 2 minus square root of 2 all over minus 2 plus square root of 2, or I suppose we could rationalize the denominator, but I'm not gonna. Cotangent of theta then would just be the reciprocal of that. And then, of course, the secant of theta is the reciprocal of the cosine, so this would be 2 over negative 2 plus square root of 2. And, of course, the cosecant would just be the reciprocal of the sine, so that's 2 over negative 2 minus square root of 2. And we have all of our 6 trig functions.